just turned that in.
Oh, is it all done?
Oh,
I
finished my
got the right answer, but not the
Okay. Let's find out. So far, what we have discovered is that for the car to go around with no friction, it has to be on a bent curve. The curve has to be angled at an angle of theta. And so what we needed to do now was, well, where do I go from here? What do I need? I need forces. In other words, I need a free body diagram. And as soon as I have that free body diagram, where am I going to take it?
Newton's laws.
Newton's laws, that's right. So let's see if we can get, no, I didn't want to write Newton. I wanted to write let's see if we can handle just the frictionless case and discover something about our car, our road in the frictionless case. Free body diagram is your idea? Take it.
Okay, we have mg going straight down, and then you have normal force going, that. And I guess that's it. Except we would have to change the force of gravity to being mg sine and mg cosine.
Okay.
Perfect.
All right. What Mac does is something that we did for a lot of our problems, which was to take the mg and to split it in components, perpendicular and parallel. For this, we use a rotated reference frame. Right? So really what he did was he rotated the reference frame. And everybody can see, sympathetically, why Mac would want to rotate his reference frame, because this sure doesn't look a whole lot like the situations that we've done previously. However, we also have a principle that guided us for choosing our reference frames. And that principle, one of the basic things, was it made a whole lot of sense to have our reference frame point in the direction of the acceleration. And the reason it makes a whole lot of sense is that ultimately I'm going to want to sum up those forces and set it equal to mass times acceleration, right? So the real rule is not rotate your reference frame every time you're on an incline. The real underlying principle here is point your reference frame in the direction of the acceleration. So now we have to ask an important question. Which way is my car accelerating? Towards the center. And which way is the center of that circle? It is directly to the left. It's exactly right. The acceleration of my car is pointing inwards towards the center of the circle so that the car can move in a circular track. So that means that although this is very tempting, what we actually want to do is to use an unrotated reference frame in this situation. Why? How would I have known that? Because I want to align my reference frame with the acceleration. So that means that actually it's the normal force that has to be split into components.
I think I did pretty much all my work with unrotated frame. I just looked at the answers.
Good. Well, that was harder. So then you have an x component of acceleration and a y component of acceleration.
Yeah. That's probably, well, anyway.
What was the reason again for splitting up the normal force?
Well, I've got my normal force pointing off at this funky angle, right? And I'm going to have to sum up forces in the x and y directions. So I've got to know how much of the normal force is in the x direction, how much is in the y direction, because what happened in the x
Say something.
exactly same. Okay. So now that just raises the important question, what are these components of Fn? And to do that, I've got to chase the angle theta around and find out where theta is. So where is theta in my diagram relative to Fn right here?
So it's
Might help to go back over to here and draw my Fn like this. Well, I'm kind of confused too, because I don't know, I see this angle theta, that's the angle of inclination, but I don't know what theta relationship theta has to Fn. So I need to do a little bit of angle chasing, right? And how do I do that angle chasing?
you use things first.
Find the right
Yes,
angle.
that's right. I'm going to need to draw myself some lines that are parallel or perpendicular to known lines. Where is a good line that I could draw? An auxiliary segment, to use the geometry term. Auxiliary line. For the Fn. That works. And if I draw that horizontal line for the Fn, then where can I find theta? Points. Like I can see it.
It's right there.
Use your words.
Is it the, on the opposite day, opposite side? No,
Here?
opposite.
Here?
Yeah.
Oh, okay. Yep. And why is that? Why is that theta?
Because theta is the same angle as that one, and that theta.
It's not. I'm getting a contradiction here. Somebody is saying it's not.
That angle should be 90 minus theta.
Why? What angle is theta?
Here.
That angle's theta? There's no way that's theta. That's bigger than 90 degrees. Oh, this angle. This little angle right here. This little angle of mine. Why is that angle theta?
Parallel line cuts another line. 1, 2, and angle.
Okay? He's good, but you need to identify these angles. What do we call these two angles? Corresponding angles, that's right. When parallel lines are cut by transversal, corresponding angles are congruent. What is the other pair of angles that are congruent when parallel lines are cut by transversal?
Alternate interior.
Alternate interior. Where's the alternate interior angle here? Z is for Zorro.
It's right, but yes, right.
Okay, it's right there. There's your alternate interior angle. This basic skill of angle chasing happens by drawing a parallel line, looking for a transversal. All of you should be able to do it because you did a lot of it last year, right?
Yeah.
Yeah. So we have corresponding angles. Doop, doop. By the way, you were the only one who got that term. And we have alternate interior angles, like so. Well, if this is theta, then this angle must be
Theta minus 9.
other way, 90 minus theta. It must be complementary.
Right.
That would be negative.
Yeah.
And
You can have another
why?
angle.
Because this is a right angle
Oh,
here.
right.
And since I prefer theta to 90 minus theta, if I want to find another theta here, I can draw myself a perpendicular. Like that. And I finally found a theta that is touching Fn, or that is related to Fn. Everybody see that? So, this gives us the material that we need for our components. Fn this way is adjacent, therefore it is which component? The adjacent component is the cosine component. And the other component, therefore, is the sine component. This process of chasing the angles and figuring out the components is a process that you're gonna need for all parts of that project. So, if you have questions, now is the time, because every one of you should be able to do this on your own. So where are your questions?
How's it a sign?
Well, honestly, I find it easier to identify the cosine component and then the other one is the sine. So if I want to see it, I go back to my Fn right here. Here's Fn, and I draw 1, 2 components, and there's the angle theta. The adjacent component is the cosine, the opposite component is the sine. I'm in this weird situation where I feel as if most of you probably couldn't do this on your own, but none of you are asking questions.
Can I get my paper back?
Yep.
Well, I did this.
Usually
I would never have thought I would
Yeah.
use, like, when I look at this, I'd be like, oh, it's on an inclination. I can just use mg sine mg cosine.
Yeah,
That's
right,
literally what I
sure,
was thinking.
right.
I would never have thought to do, oh, I can do this for f.
Okay, that's why I sent you all those hints. Because once you start looking at, for example, the example problem in the book, they do exactly this.
I figured it out by the
Okay, so you're using the normal force because it's friction.
Yeah. I'm using the normal force because the normal force is there.
It aligns with the y-axis.
You mean I'm finding components for the
Why
normal force.
why didn't you use
The rotated reference frame?
I think it's condensate. Yeah, why didn't you use
I didn't use the rotated reference frame because the direction of the acceleration is straight to the left. And so the underlying principle is we're going to align our coordinate axes, our reference frame, so that it points in the direction of the acceleration. And the reason we do that is that ultimately we have to say sum of forces equals mass times acceleration. So I have to be able to do a sum of forces in the direction of the acceleration to do that conveniently. Yes, ma'am?
I just kind of
Yep. Yes.
So, is it true that, so it's not always like cosine theta is the y-axis and sine theta is?
Yep.
Okay, because I was making that assumption for both Vmax and Vmin,
Uh-huh.
and it worked out for Vmax, but not for Vmin. And that's probably where this comes into play.
Maybe so. Yeah. So we used cosine for x and sine for y components way back in the vector thing. But we did that because we were always measuring our angles from due east.
Okay.
And now the angle for Fn, not the angle for the incline, that's
Mhm.
due east. The angle for Fn is actually measured from north.
Okay.
And because that angle is not measured from the same reference frame, I can't use the basic x equals cosine component. Instead, I have to do the adjacent and opposite components, which are the real underlying trig components. Yes.
So I'm at a stage where if you give me a question, I might not be able to figure out how to do it myself. But if I see an explanation, if I see the answer, I'll
You
say,
can
okay,
follow
that
it.
makes sense.
Yeah. Yep. How many of you are at the I can follow the explanation stage that we got here? Okay, that's good. All right. Now how to get there from there is to explain it to yourself in terms of big picture ideas. You explain to me, in your own words, what's the big picture that I used to get from here in black to here?
What you basically from the angle of the force, and then you can figure out cosine and sine.
That's it. You got it. That's the whole deal. We figure out the angle, which we do by angle chasing. We draw for ourselves parallels and perpendiculars as needed until we found an angle that was actually touching Fn. Angle theta actually touching Fn. And then we simply asked adjacent and opposite. Also, you can check yourself really easily. You want to know how to check yourself?
Sure.
Take the extreme case. Take the case of theta equals 0. And when theta equals 0, Fn should be pointing straight up. So that Fn in this direction should be Fn. Fn in that direction should be 0. One of our trig functions has a value of 0 when theta is 0, and that's the sine function. So when theta is equal to 0, sine of 0 is 0, cosine of 0 is equal to 1, which means that when theta is equal to 0, I should get Fn, all of Fn this way, and 0 Fn that way. And that checking works so well that sometimes I just cheat and use that to figure out which one is my sine and my cosine without chasing any angles. Yes?
Is Fn sine theta always perpendicular with mg?
Fn sine theta is always going to be opposite to theta. That's the best way to think of it.
So how did you know to make Fn sine theta like a straight line through the triangle? Or through the...
Well, any vector. So, let's say I've got some reference that looks like this. And I've got some random vector that looks like that. And I want its components. The components are the vectors that align along the axes to add up to this guy. So in other words, the components are going to go along this axis and then perpendicular to that along that axis. So it's the amount over and up in your reference frame. So to get the components for Fn, I went up the y-axis and over along the x-axis.
So that would be your free body diagram.
This would be my free body diagram. Flow of friction.
So nothing, no other force.
No other forces. Yep. Yes, ma'am.
Can I ask
Oh,
you a
just for
question?
different-
Yeah, go ahead.
Can I ask about something later on in the problem?
Yes, I'm going to leave this here, but go ahead and ask.
Okay, so there's one point, I think it's in, I'm not sure if it's in both VMAX or and VMIN, but I think it's in VMAX, where you have to equate the normal forces. And I don't understand why.
How about normal and mu times normal? Or something like that?
I just know this one explanation that you have to equate them, like that doesn't make any sense.
Yeah, that doesn't make sense to me either.
It's just saying that the force on the x direction is equal to the force in the y direction.
That's not true though.
I interpret as they're not moving both directions, so both of them are supposed to be equal to 0.
Oh, both of them are 0. Oh, interesting. I see. But they're not both 0, because the force in the x direction will be v squared over r. In v squared over r.
It's not changing the station.
Oh.
Yes, it is. It's going around the circle.
Yeah, because cosine is 0.
But the x is not like going, it's not slipping towards the center or towards the outside.
Yes, you're correct. It's not slipping towards the center or the outside, but it's still going around the curve.
It's an x. It's like the force in the x direction. It's not. It's in 0.
Well, so the x direction is probably a misnomer. It's really the centripetal direction, right? And that centripetal direction is changing as we go, so there has to be an acceleration going on.
Right.
Yeah,
Zero force.
has to be. Otherwise, the car wouldn't go in a circle. It would go in a straight line. Objects with 0 force move in straight lines with constant speed.
Oh, also, why is A towards the center, not on the bottom of the line?
Great question. So if the A were in this direction right here, then the plane of my circle would be along the incline, and the car would actually be driving underneath the ground and back up.
That's
So the plane of the circle is actually horizontal. The road's like so. And the center of the circle is directly towards the center of that plane. Okay? Yeah, good. Now what I have not done for you, I did help you out with your components right here, but what we did not do is we did not find a relationship yet between V0 and theta. And the reason that we did not find a relationship between V0 and theta is that we got to the free body diagram point, but we haven't done what yet? Newton's laws. And that's the missing basic thing that's going to get you your relationship. So for tonight, if you have not already completed this project, or if you are not sure about your work, your job is to find the relationship between V0 and theta by applying Newton's laws here and seeing what you get. Okay? Good.
Wait, that's just tonight's assignment?
That's just tonight.
So what about what it says on
Oh, that too.
oh, that's it,
Yeah.
okay. Just making sure.
And at this time, we're going to shift gears and we're going to talk about work.
About what?
Work. Not homework. Work. Physics work.
Oh,
That's exactly right. Our story so far has been a story of kinematics, or equations of motion, and forces that cause that motion. And with our kinematics, we had basically two models of motion. We have described all motion so far as either motion with constant acceleration or motion that was uniform circular motion. Not every motion is like that, but these are the two basic models that we've used as simplified versions of motion. To do more complicated models of motion, we need calculus, and we don't do that in this class. Take AP Physics for that. Now, actually the calculus makes it easier. Believe it or not, physics with calculus is a lot easier than physics without. So you guys are doing hard work at this time. I mean, think about it. If you know derivatives, isn't it easier to see all those equations way much? Way much easier. See? There you go. So, and then we had a story of forces, which was really a story of Newton's laws, and we analyzed everything in terms of free body diagrams taking us to Newton 1 or Newton 2 that gave us an acceleration. And that's it. This is the whole year so far on one page. Ta-da!
That's all we got.
It feels like so much more.
But there's a whole lot of detail, isn't there? That's right. But
Wait, so we just gone over two things.
But two really important big ideas that require a lot of detail. You're going to do the same thing in calculus. I just have two big ideas in calculus: derivatives and integrals. The end.
The whole year?
The whole year.
Two jokes.
But then we fill out all the details.
Wow.
Years.
We fill it all
Big
in.
deals, so.
So we can't just like.
But why do I simplify it so much? Why do you think it's important that I take the whole year and I put it in such simple terms? Hint, it's not to make you feel stupid, because you're not stupid. What am I doing?
So you understand?
And what kind of understanding in particular? The big picture. I'm giving you big picture understanding.
That's what Mr. Stewart.
So that when you approach a problem, you're going to say, okay, what's the big picture? Well, so far our big picture has been free body diagram. Newton's laws, equations of motion. That's it. The same process every single time. And that helps because it gives you confidence. Oh, I know how to do this. And we all need some confidence in that, right? So, what we're going to do now is we're going to take the same idea of forces, but instead of approaching it from a kinematics perspective, we're going to approach it from an energy perspective. Now, let me explain. Kinematics has to do with the motion of an object through time. Notice the variable that shows up in my equations of motion here, and that variable is the variable of time. So that I'm describing how the object changes its position, how it changes its velocity over time. But in many scenarios, I don't know how long it took for the object to go, but I do know how far it went. And so I'd like to be able to analyze the motion of the object in terms of distance traveled instead of how much time it took. So we're going to shift our focus from the time domain over into the distance domain. And to do that, we're going to compute two simple quantities, work and kinetic energy. So, So what we're going to do then is we're going to relate the effect that a force has on an object as it travels a distance d to the motion of that object. When an object travels a distance d, so picture it under the influence of the force right here. Here's my object at mass m. Because the object is experiencing this force, use your prior knowledge here, what will that object experience as a result of the force? Acceleration. And as a result of the acceleration, what's going to happen to its speed? It's probably going to increase it. The only way that wouldn't happen is if the object were already moving backwards. In that case, the force would slow it down. But let's assume that the object starts from rest. Let's say that the object starts from rest, and that means that the v0 will be 0. And we're going to say that the final velocity of the object is going to be v. We don't know what v is. The picture you want to have in your mind is that the object is going to have a velocity of 0 here, and it's going to have a final velocity of v. Now we're going to compute force. We're going to compute the product of force times distance, and we're going to call that the amount of work done by the force. So here's going to be our basic definition of work. We're going to use the symbol W for work, and we're going to call that the product of force times distance. Notice that work is measured in newtons times meters. That's kind of weird. We haven't had any times units before. Newton meters.
Sounds like to get on to
And 1 Newton times a meter, we're going to also call a joule. 1 Newton times a meter is, we're also going to call a joule.
So Newton's times meters is a joule. Doesn't matter what. It's like the Newtons like come in different forms, like kilograms times meters per second squared, and then like something else.
Right, right. So newtons themselves could be rewritten as kilogram meters per second squared. So that, strangely, my units of force times distance are also kilogram meters squared per second squared. Huh, that's kind of wild. But it's not too terribly strange, because we know what a newton is. What's that? Yes, a joule is a unit of energy. So now we need to talk about what this energy thing is. And here's going to be our definition of energy. Energy is the capacity to change the speed of an object. Notice I did not use the word velocity here, and that's going to be really important. What we're going to find as we work in the distance domain is that I'm going to be able to say things about the speed of objects, but not necessarily the direction. Do we all agree that this force here applied over this distance is definitely changing the speed of the object? So the work then would be fit into the definition of energy. It's the capacity to change the speed of the object. Well, that immediately raises the question, how much change in speed do we get? So let's actually do a computation, because we can do that. We have one equation of motion that does not involve time. Do you remember what it is?
V squared equals the initial square
Mhm.
plus 2a times change in
Yep. Now, how much change in speed do we get? Let's use that kinematic equation that Mac just gave us. V squared equals VO squared plus 2a change in x is our kinematic equation. But now we're going to have to replace some things, because we didn't call the delta x, we called it d. So let's do that. And we didn't have an acceleration. What we had was a force. We can replace the acceleration with force over mass. And we had 0 initial velocity. So that when I plug in all those things, what I get is v squared equals 2 times f over m times d. Everybody with me so far?
So
Just replace-
acceleration equals force over mass.
Sure, because f equals ma.
Is that why we don't do
Oh, that's easy.
Yeah.
Is that why we don't do a lot of velocity, because the distance is an absolute value? Oh wait, no.
No.
The delta actually.
I mean,
We're
yeah.
doing lots of velocities. You're okay. But now, I observe here this quantity f times d that I already considered the work. So let me isolate that quantity by dividing both sides by 2 and multiplying both sides by m. And when I do, I get m times v squared times a half, here's dividing by 2 for you, equals f times d, which is the same as the amount of work that was done. Now here's what I'm going to do. I'm going to call this quantity here on the left-hand side, I'm going to call that quantity the kinetic energy of my object. Objects that have a speed have a kinetic energy. Yes.
What you get from that?
I divided both sides by 2.
So you're calling the mass.
No, the whole quantity right
Oh, the
here.
whole.
Definition, we're going to call the kinetic energy of the object 1/2 mv squared. Now, in what sense is that energy? The capacity to change an object's speed. Well, it's kinetic energy like this. Everybody watch Watch this carefully. Ready to catch?
Yeah.
Watch his hands, not the pen, watch the hands.
Oh, yeah.
Okay.
That didn't work.
Let's try again, here.
Alright.
Here.
Whoa.
Watch the hands.
What? It's going like so weird. It's like, okay, here. Alright.
Okay, good, all right. Now, he did a little bit of moving himself, but I want you to notice when that pen hits, it changes the speed of his hands, doesn't it?
Seemed to
It
like
transfers kinetic energy. The pen transfers some of its kinetic energy to his hands and changes the speed of his hands. One thing.
Right there. See, it's hard.
There, it's hard. And two hands. Right hand.
So,
If you try some heavier
for, friend request, and then what you say,
Sure.
this equation will assume that initial constant is always zero.
No, we won't necessarily assume that. And if I had not necessarily, I will develop that tomorrow. Right. But here's the main points that I want you to catch at this time. We're going to compute these two quantities that seem to be related to one another. And the first is we are going to compute the amount of work done by a force, which is going to be force times distance. And then we are going to compute the kinetic energy of an object, which is 1/2 mv squared. These are the two formulas that you want to walk away from today's class with.
So then,
And what I'm claiming with my little blurb in blue here is that those two quantities are actually closely related. That anytime you do work on an object, what you're really doing is adding kinetic energy to that object. And that's what the equation tells me. The work that I did was equal to, I started with 0 kinetic energy, and I added 1/2 mv squared worth of kinetic energy to the object.
that's what I was gonna ask.
Yep. But I'll develop that idea tomorrow, and we'll have a lovely theory, a work energy theory. Now, there are a couple of wrinkles when you're computing work. And the wrinkle that when you're computing work is that we don't always have a situation where my force is aligned with the distance that I'm traveling. So I want to consider that at this time. I want to consider what happens if.
Can you see that one?
Yep. I want to consider this situation. Where I am going to take a force that is at an angle theta and I am going to apply that force as the object slides a distance d in the horizontal direction. And my question is, how much additional energy am I adding as a result of this? Well, you probably know where this is going. Components. I need to consider the component of the force that is in the horizontal direction, Fx, which is adjacent to the angle theta and is therefore F cosine theta. And I need to consider the component of the force that is in the vertical direction, which is Fy or F sine theta. Okay? Now, you guys have been around the block enough to know what other forces are acting on this object other than Fy, other than normal force, Mg,
G friction.
and you have pushed enough blocks to know what's going to happen in the Y direction. Nothing. There will be no motion in the Y direction. All of the Fy is wasted as far as adding energy to the object is concerned. Only the Fx, the component of force in the direction of motion, adds any energy to the object.
So push.
Let me say that again, and then I'll take a question. Only the component of force in the direction of motion adds energy to an object. And here's the way to visualize it. I've got my force, I've got my distance. Here's my force vector, everybody sees that. Here's my distance vector. and only the component of force in the direction of motion, let's call that F parallel, because it is parallel to the direction of motion. This is the only component of force that actually does any useful work. How do I compute it? Well, it's real simple. The component in the direction of motion is adjacent to the angle between, and therefore is the cosine component. So that my real formula for work is this formula right here. Work is equal to force times distance times the cosine of the angle between. Where theta is the angle. It's not the angle that the force is from due east. It's not the angle that the distance is from due east. It is the angle between F and D. And what's nice about this formula here is that it is reference frame independent. I don't have to choose a particular reference frame in order to figure out the angle between the two.
What if the force is coming from something like a golf club hitting a golf ball in the air?
Awesome. So a golf club hits a golf ball in the air. Here comes your golf club. Let's say it's a wedge or something like that. Here comes the golf club. Here comes the golf ball. The golf club is going to hit with a normal force, right? It pushes in this direction. And the ball also is going to move in that direction. And so that means, in this particular case, all of the force is parallel to the direction of motion. And therefore, all of the force is going to do useful work. And therefore, the work is simply F times D. If I were to use this formula, I would say the angle between the two is 0 degrees. And the cosine of 0 degrees is 1. And therefore is invisible. So this is one special case. Before you guys go, I want to give you 3 special cases, real fast. If F is exactly parallel to D, then the angle between them is 0, and the cosine of 0 degrees is positive 1, and therefore work is simply F times D. The 1 is invisible. This is a big special case that we love. If F is perpendicular to D, for example, a normal force, then the theta between them is 90 degrees, and the cosine of 90 degrees is 0, so that work done is automatically 0. We love that special case. Perpendicular forces never do any work. And then third, if F is opposite of D, or anti-parallel to D, then theta is 180 degrees. What's the cosine of 180 degrees? Negative 1, that's right. So cosine theta is negative 1. And the work done will actually be a negative quantity, negative force times distance. What does that mean, negative work? Well, I'll explain tomorrow, but it means that the object is slowing down.
Can you move it up just a tiny bit?
Yep. I'll put these notes out
Thank you.
and see you tomorrow.
What is the box?
Yeah, yeah.
Okay.